Welcome back. In the second part of this video, we'll set up the main fire explosion. There is a lot more going on here. First, I will unhide the layer that has the liquid simulations, but leave only the particle containers visible. Since I'll be using those particles as emission sources, I need to keep them visible. That is because by default, Phoenix ignores the hidden objects. You can, of course, change that behavior by going into the Scene Interaction rollout and disabling the Exclude Hidden Objects option. Personally, I like keeping it on because I find the ability to quickly hide and show objects a lot more convenient than going into the Include-Exclude list each time and constantly adding or removing objects from the list. But this really is a matter of personal preference, and Phoenix gives you the option to change it if you prefer. For example, here I kept the Exclude Hidden Object option enabled, but I switched the list behavior from being an exclusion list to include and interact only with the objects that are listed unless they are hidden. This means that I need to manually add stuff to the list whenever I decide that I need an additional source or perhaps some turbulence force or a voxel tuner, etc. But at the same time, if I accidentally leave some unwanted objects visible, like parts of the environment or anything else, I don't need to worry that they'll mess with the simulation. Generally, it is a good practice to make your simulations inside a simplified scene and merge it into the scenes used for rendering when they are finished. But also, sometimes you may want to do a quick test render while you are tweaking the sim settings. So the Include-Exclude list is a great option to define which objects are important for the sim and prevent it from interacting with some heavy assets that perhaps have opened edges and therefore are unsuitable for simulation use. Okay, let's now take a look at all the different elements that are used for this sim. There are several Phoenix sources, as well as a couple of voxel tuners and turbulence forces. I'll change the output path so that I don't overwrite what I have simulated so far. And I'll disable all of the sources and leave only the first one. Let's go from top to bottom. The first one happens to be the source for the burning cloth. It has a copy of the TieCache cloth object added as an emitter node. This instance of the cloth object also has the shell modifier, but also a push modifier on top to make it even thicker. That's because this time I decided to use the volume inject emission mode. There is no particular reason why I chose the volume inject over the surface force. I just tried it both and decided that I like this one better. Also, I could have used the existing shell modifier to make the cloth thicker, but I decided to leave it with the original thickness and add the push on top and play with the push value and have the ability to quickly turn it on and off if I needed to. This time, the cloth source isn't masked with the black and white bitmap, and the entire object will emit temperature and smoke. I also enabled the RGB and set it to a dark gray color. This will affect the color of the smoke. And in order to save this into the simulated cache files, the grid RGB needs to be enabled in the export options. Go into the output rollout and enable the grid RGB. The emission power, the temperature, and the smoke are linked to a discharge modifier. I named this modifier emission speed. It multiplies the channel values that it is linked to by the speed of the cloth's vertices. That way, the cloth will stop burning once it rests on the floor. To be fair, the cloth, being soaked in fuel, might keep burning when it sits on the ground. And to do that, you simply have to raise up the discharge value at speed 0 so it will keep emitting with a reduced force while the object is stationary. I also animated the emission. The temperature and the smoke amount to ramp up in the beginning so that that part of the sim blends better with the flames from the first simulation. The injection power goes up from 0 to 50. The temperature rises from 300 to 2500, and the smoke goes from 0 to 0.5. The next two sources are for the fragments of the bottle and the trails that are left behind. First one is using the exported tie cache of the broken bottle as an emission object. Some of the pieces are really tiny, and if you go into the simulation's preview settings and enable the Show Graph Cells option, Phoenix will display the size of the voxels. The size of a single voxel is just 8 millimeters, but still, there are pieces that are smaller than that and won't contribute much for the emission. You can of course add a push modifier and make it bigger, but I think that it is better if you use the same culling option as before and get rid of it. This source is also using the volume inject mode. And the injection power, the temperature, and the smoke are linked to the same discharge modifier as the one used for the cloth, meaning that they'll emit more when they fly faster and less when they are resting on the floor. The injection power is animated from 0 in frame 72 to 200 in frame 75. At some point, however, I noticed that those pieces alone won't give me the nice trails that I was aiming for. So I decided to make some additional TieFlow particle system. This new TieFlow is using a birthflow operator to bring in the cached bottle pieces, and then spawns new particles based on the traveled distance. The new particles don't have a shape and they live only for 10-15 frames. The fragments trail source has this new TieFlow system added as an emitter object, and it emits temperature and a small amount of smoke from the particles with a lower injection force. The size of the particles is set to be as big as 1 voxel, and the motion velocity amount is reduced to 0.1. The reduced velocity will help the fluid to stay behind as a trail and not trying to move forward along with the particles. The temperature value and the smoke amount are animated again, and the timing is set to absolute. Both of these sources emit dark gray RGB colors. We'll talk about the colors later when we look at the shaders. The next two sources on the list are called fuel mist and fuel splashes. As the name suggests, the first has the mist particles form the first cascade added as emitters, and the other one has the splash particles. Both emit fuel, but they have slightly different settings. I'll go through the settings in a minute. Let's first go into the fuel rollout. In order for the fuel to ignite, you need to click the Enable Burning checkbox. This will make the emitted fuel ignite once it reaches the right temperature, and while it is burning, it will produce smoke, raise the temperature even more, and also expand based on the energy and propagation speed settings. As an option, you may also want to go into the output rollout once again and enable the grid fuel checkbox. This will write the fuel channel into the cached files. But you have to do that only if you are planning to use the fuel channel for something later. For example, you may want to use it as opacity for the smoke, or visualize it along with the smoke using an additional voxel shader, or simply check what it looks like as a preview. If you are not planning to do any of that, you can keep the export fuel option off. It won't change anything for the simulation. It will still burn. Sure, you won't be able to use it later, but you'll have smaller cached files and a slightly faster simulation. Okay, let's now take a look at those settings. Both emitters are particles with the size of 1 voxel. They both emit some fuel and some smoke. And the RGB channel is a slightly brighter gray color. This will be the color of the smoke that is emitted directly from the particles even before the fuel starts burning. The one with the splashes uses the injection mode, and the injection power is set to a small value of 1. This one also has some temperature that is slightly above the default 300 kelvins of the simulation grid. I chose this value because I set the adaptivity of the grid to be based on the temperature and the threshold is set to 301. I could have based it on the smoke or the fuel, but the smoke might dissipate and the fuel will eventually burn out. There is also an option to use the speed channel with a lower threshold, so that whenever there is anything moving through the grid, even slowly, it won't shrink and clip some parts of the simulation. But I didn't want to experiment with the speed values and try to find the correct threshold, so the temperature channel was the more convenient choice. So the splash particles, having temperatures slightly higher than the adaptive grid threshold, is what forces the grid to expand initially. The motion velocity is lowered to 0.1 because of the same reason as before. It produces nicer trails instead of the mushroom-like plumes. The mist particles are using the volume brush mode with the strength of the brush effect set to 50%. The brush effect will try to push the values inside the voxels towards the specified values. If it is set to a 100%, this will happen instantaneously, and with a lower percent, it will be more gradual. There is one very important thing to keep in mind when using the brush effect mode. It works both ways. For example, if you are brushing smoke with a small amount of 0.2, but the voxel already has a lot more smoke, perhaps coming from other sources, the brush effect will start reducing the smoke amount towards the value of 0.2, and this goes for all of the channels, even the temperature and even the speed. This means that when the fuel ignites and the temperature starts rising, the volume brush particles will try to lower the temperature back down, messing up with the burning process. And this also means that if you try to volume brush with a reduced motion velocity value, it will slow down everything inside the voxels where the brush particles are. Because of that, I switched the temperature emission for this source off and also disabled the motion velocity. In the fuel rollout, currently all of the settings are at their default values except for the ignition temperature. The temperature that the fuel needs to reach before it starts burning is set to 1600. Beyond that point, it will start producing smoke and heat, and it will start expanding. The amount of heat that is added with each step and the amount of expansion are controlled by the energy parameter. How fast this is happening is controlled by the propagation speed, and as it burns, it will start depleting with the specified rate. Currently, there are just the two fuel sources active in the scene. The first one isn't adding any temperature, and the other one is adding just 305 kelvins. And that's not even close to the temperature needed for fuel ignition. Yet, as the simulation goes, you can see that the temperature rises even without additional heat sources present. And the flames start to appear even before it reaches the 1600 threshold. So what is happening? The culprit is the first one of the voxel tuners. It says that if the fuel amount is greater than 0.001, the temperature should rise by 50 kelvins on each step of the simulation. This simulation runs with 3 steps per frame, so it will rise with 150 kelvins on each frame. Let me quickly explain what I mean with a simple test scene. Here, I have a phoenix source that is volume brushing some smoke inside of a sphere. It's just the smoke. Everything else is disabled. When you run the simulation with the tuner disabled, the temperature stays at the default 300 kelvins. The tuner is set to increase the temperature by 1 inside the voxels where the smoke is. And if you enable it and run the sim again, you can see that the temperature starts from 301 in the first frame and reaches 320 on frame 20. If you, however, set the steps per frame to 5 and run the sim again, the temperature increased by 5 on each step and will reach 396 kelvins in frame 320. So you have to keep that in mind. Back in our original setup, the first tuner says, if there is even a small amount of fuel in a cell, start heating it up. And if you look at the shader, you can see that the brightest point is slightly before the 1600 mark, making the temperature to emit light even before the fuel catches fire. As I mentioned before, once it does, it heats even more rapidly, and the values go towards the right part of the diagram, where we have these deep red-brownish colors. But before that, we get this really bright edge of not yet ignited fuel. This, of course, is a hack. In reality, the burning cloth is what's supposed to ignite the fuel, and normally, the energy and propagation rate would take care of the rest. I added this additional tuner, however, only because I wanted to have better control of that process, and eventually I liked how it turned out. I was able to ignite all of the fuel and get this rolling flames effect even without raising the energy and propagation speed values. If they were raised too much, the fuel would have expanded, making it look more like an explosion instead of having this creeping flames look. The second voxel tuner in the scene is more of a tweak. It deletes the fuel by setting it to 0 when the temperature reaches 1800 kelvins. Normally, the burning process will deplete the fuel naturally, but remember, there are particles underneath that are constantly brushing and adding more and more of it. So this simple rule set by that tuner says, when it is hot enough, that's it, no more fuel. This helps create this spot in the middle that grows and eventually forces the depletion of the fuel. There are many different ways for achieving this. You can, for example, hand animate the particle emission, stopping it from releasing fuel, and then adjusting the fuel depletion parameter and make the depletion rate slower or faster. But the tuner seemed like a nice trick, so I stuck with it. And finally, the last two sources, the wall and the ground. These two take care of the burning wet spots. Similar to the previous two that were using the particles from the liquid simulations to add fuel, this could have also used the wet map particles directly as emitters. But since this project was intended to showcase a diverse set of options and possibilities, this time I decided to take a different approach. I added the collision geometries as emitters and masked the emission area and temperature using Phoenix particle textures. The one for the wall has the column, which is a simple box, and the one for the ground has a retopologized and simplified version of the curb, and the floor that is again a simple box. The first instance of the particle texture is reading the wet map particles of the first simulation cascade, and the second one is reading the wet map particles from the second cascade. The render time only option needs to be disabled so that Phoenix can see the result of that node during the simulation. I used the proportional blending method, and the radius is animated to go from 0 to 10 for 10-15 frames, starting at frame 0. The particle age checkbox is enabled so that the animation can be evaluated for each particle, starting from the moment of its birth. By having these two separately and having two separate Phoenix sources means that I could have plugged each one of the textures into the mask slots of the corresponding source. But I decided to combine them with a V-Ray comp texture. Then I took a simple noise and multiplied it on top using another V-Ray comp texture. The noise is set to fractal, and the phase is, of course, animated. But the most notable change is that I set it to use the world coordinates. That way I didn't have to worry if my objects have UVs and if they are going to have different scales and so on. Setting this to world XYZ forced it to have equal size on all objects in the entire scene. The combined result is used as an emission mask in the sources. And an output node with lifted black values is plugged as a temperature mask. Having the two wet map textures combined also meant that I could have used a single Phoenix source containing all of the emitter objects. But I decided to keep the column in a separate one and have the option to tweak the settings and timings independently if I needed to, or perhaps hide the one while tweaking the other. But doing this one way or the other is a matter of personal preference, and it is up to everyone's choice how they wish to set it up. Let's now quickly go through the settings of the second simulator itself. The bottle hits the wall in frame 71, and that is set as the simulation's start frame. There is no point simulating before that. The grid is rotated and the z-axis is pointing forward, away from the column, instead of up. I did this only because when you adjust the x and the y dimensions, the grid expands in both directions. But changing the z size, despite where you place the pivot, takes the bottom of the container as a base ground level and only adjusts the height of the grid. This is very convenient in most situations, but maybe not in this one. So I flipped it on its side. This doesn't affect the simulation in any way, and I only did this for my own convenience. The grid is placed where the point of contact is, but it is not parallel to the column. It is rotated 20 degrees. And that is only because some of the pieces fly away to the back too much, and it made more sense to orient it that way. As a starting point, the grid is 100 by 100 voxels wide and 90 voxels tall. This gives us an initial resolution of 900,000 voxels. And since the scene scale is set to 4 and with a voxel size of 0.8 centimeters, This gives us an initial grid size of 320 by 320 centimeters. As you all know, the scale of the scene is probably one of the most important parameters in every dynamic simulation, and Phoenix makes no exception. Generally, it is a good idea to model your assets and build your scenes in the correct scale, and that would give you the most realistic results. However, if you are working on a scene that is slightly off scale and is impossible to correct, maybe because you already have some procedural noise textures in there, or maybe you have a camera depth of field that is already set and you don't want it to change, or even if maybe the lighting is already set and might change if you scale your assets because of the light decay options. In situations like these, the scene scale parameter inside Phoenix can give you the option to compensate for the incorrect scene scale and make the simulation appear and act as if it is in a scale different from the one that is in your scene. This particular scene is modeled in the correct scale though. But despite that fact, I increased the scene scale parameter to 4 and artificially forced Phoenix to simulate as if it was 4 times bigger. This was an artistic choice. Sure, the correct scale is important, but it is also a tool that you can play with and get different results. At a larger scale, the flames and the smoke will move slower since they travel more distance, and I liked that effect and decided to break the rules a little bit. So despite the fact that the actual dimensions of the simulator are 80 by 80 by 72 centimeters according to the scene, internally it will behave as it is 4 times bigger. The timescale is set to 0.25 to match that of the liquid and the first fire simulations. I settled on a cooling value of 0.085. This will force the fireball to cool more rapidly and will prevent it from rising too much and too fast. The rate at which the smoke dissipates is slightly increased. It is set to 0.1. The fluidity conservation method that is used for that sim is different from the one used for the cloth on the flying bottle. It is set to PCG symmetric. That is one of the benefits of splitting the simulation in 2 separate grids. You can use different resolutions, different settings, and different conservation methods for each one. Also, the PCG symmetric is the method that currently supports GPU acceleration for the simulation. If you have a powerful video card and choose the PCG symmetric, you can enable the Use GPU to aid simulation option and get significantly shorter simulation times. The PCG symmetric also has a very strong conservation and is generally great for explosions. The main challenge with this part of the setup, however, was to have a nice and curly look at the beginning and then transition into smooth flames. That is why I increased the vorticity values in the beginning a lot and animated it to go down to a much smaller values. This is also done for the quality of the conservation. It is animated from 160 at the start of the sim down to just 10. Higher conservation quality value will help keep the velocity and the vortexes that are created for longer at the cost of the simulation time. It is worth pointing out that these values may be tweaked to your liking and for the needs of your project. Increase or decrease the cooling rate if you want the flames to disappear sooner or linger for a longer time. Increase or decrease the smoke dissipation rate based on how much smoke you have emitted in the first place and how much of it you wish to keep until the end. Play with the vorticity that will greatly affect the look of the flame and smoke. Increasing the quality of the fluidity conservation will help the fluids travel further before they dissipate. However, since the conservation is based on the number of voxels when the resolution is lower, the fluid will travel further away, even with the same quality value. So if you decide to lower the resolution, but still want the velocity to cover roughly the same distance as with the higher resolution grid, the conservation quality has to be reduced as well, and vice versa. And finally, let's talk about the emission curve inside the volumetric render settings and how to get more details out of the fire. I've prepared this scene with a simple fire in it. But even though the resolution is about 20 million voxels, the fire doesn't look that detailed. And even if you try rendering this out, it is no surprise that it will look quite similar to what we had in the viewport preview. It has no detail in it, and the smoke is brightly lit by the flames. I'll close the IPR and open the volumetric options to see what the default settings are. There is a flat line starting at 800 kelvins and 0 light emission, going up to its brightest at the 3000 kelvins mark. The temperature range inside the current cache file that is loaded doesn't go all the way to 3000. The hottest part of this flame is at 2500 kelvins, as shown by the teal color on the diagram. There is a color gradient above the curve. The coldest parts of the flames are colored in red, and the hot parts on the right are colored in orange. The color of the smoke is set to be a consistent middle gray color, and the controls for the smoke's opacity are set to simple smoke. You can go into the Phoenix rendering rollout and load one of the default presets available. In here, you can also save your own presets and use it later in some other projects. I'll skip that option for now and use one of the preset that comes with Phoenix. I'll choose the fire preset, and Phoenix will warn me this will overwrite all of my current rendering settings. I'll agree to that, and right away, some definition in the flames will appear. I can quickly go through the settings and inspect how the emission curve was changed along with everything else. The hottest parts of the flame that sit on the right side of the diagram are clipped, and the brightest point is set to be at 1280 kelvins. The controls for the smoke opacity are changed from the default simple smoke to temperature, but this is irrelevant since the rendering of the smoke is disabled entirely. I'll bring the IPR window back and check how this looks like. It definitely needs some adjusting. This preset can be a great starting point, but for the sake of the tutorial, let's reset all of the rollouts back to their default states and try to build something similar from scratch. I'll turn the GI off for a moment in order to get a faster render updates in the IPR, and also turn off the smoke and focus on the flames. The flames will become even brighter, and this red color shows where the flames are at the 800 kelvins mark. I don't really like that, so I'll grab that point and slide it to the right. Also, grab the right point and make the curve steeper and the transition from bright to dim sharper. The Phoenix source that I used emits temperature of 2500 kelvins, which is here at the bottom and on the right side of the curve. Currently, it is very bright, so I'll double-click on the curve to create an additional point and move it here so that I can clip the hottest part as well. This had some effect, but it looks like the flame is still very bright at its hottest point. And the reason for that is the physically based value. The physically based model is based on a real-world black body radiation measurements, and these are multiplied on top of the curve that you are tweaking. In order to have full control over the way the flames look, you need to disable the physically based multiplier by setting it to 0. With the physically based option turned off, the flames aren't that bright anymore, but you can compensate for that by adjusting the fire intensity value. The first layer of voxels that are near the emitter will always produce this sharp and visible boundary though. You can lower the opacity by using a distance texture. In the material editor, I have one distance texture prepared that has the emitter object already added. The color near the object is set to black, and the color that is far away from the object is set to white. This texture is put through a color correction node so that the contrast of the gradient can be adjusted if needed. It can be plugged into the modulate texture slot for the fire. It will immediately set the opacity of the fire inside the voxels near the emitter to 0. You can play with the distance and also with the sharpness of the transition. Depending on how you are planning to use this render, you may switch the opacity mode from fully visible to use own opacity that will give you an alpha channel that is based on your opacity curve. This might help you if you decide to composite the flame in an external application such as Fusion or Nuke. In Use Own Opacity mode, a few other options will become available, such as the ability to multiply a texture over the opacity. You can use this to plug the distance texture here and leave the modulate slot available for something else. I'll slide the orange color to the left and place it near the brightest point of the curve. And I'll get the red color and place it on the other side of the orange one, making the bottom of the flame even less bright. This might seem counterintuitive, but in reality, most of the time, the fire is less bright and more transparent near the object that is burning. That's because there is always some sort of material acting as fuel. Regardless if it is wood, gas, or something else, the material evaporates. And as it burns, it produces more and more energy until it is depleted. In Phoenix, though, we have the convenience to skip the fuel component entirely and generate heat directly from the object. This simplifies the process significantly and is quite handy, but you need to make these adjustments inside the shader so that the flame looks more realistic. I'll re-enable the rendering of the smoke and switch the global illumination back on. The smoke will now be illuminated by the flames. And I can now switch the opacity mode from simple smoke to smoke, and this will unlock the curve where we can additionally tweak it. And of course, the fire glows, so I can enable the lens effects in the frame buffer. And I can go into my camera settings and enable the motion blur. As I'm getting closer to the desired look, I can keep making some minor adjustments to the curve and the colors. Making the colder surface of the flames brighter than the hot core helps to define the shapes and makes the details more pronounced. And of course, you can add some adjustment layers inside the V-Ray frame buffer and fine-tune the exposure, contrast, saturation, and so on. The exact same principles are applied to the Molotov explosion. The emission curve spikes at around 1550 kelvins. There's a bright orange color near the curve's highest point, and some dark red-brown colors on each side. A distance texture that has all of the objects that emit temperature directly is added to the multiply opacity texture slot. The smoke color is based on the RGB channel and is using the colors emitted from each of the sources. The opacity of the smoke is just a line going from 0 to 1. And I believe that that's pretty much it. I hope you enjoyed this video and that it was useful and informative, and that you learned more about Phoenix and some concepts and techniques related to grid-based fluid dynamics in general. I believe that combining these techniques and applying these principles, you'll be able to achieve a wide variety of effects. Don't focus too much on the exact values shown in this video. Use your knowledge about how different settings affect each other to build your setups. Explore Phoenix and the wide variety of options that it provides. Thank you for watching, take care, and goodbye!